Hello friends. So today we are going to continue with the 2019 mains questions, and so this is for part 3 of 2019 mains, and total there are 8 questions of it, and along with it we are also going to solve 2 questions from 2020 mains. Okay. So in total you can say there are 10 questions. So in the first question, it was asked in the year 2019, and it states that a rectangular coil dimension 5 cm by 25 cm with 100 turns carrying a current of 3 ampere in the clockwise direction is kept centered at the origin in the xy plane. A magnetic field of 1 Tesla is applied along x-axis. If the coil is tilted through 45 degree about z-axis, then the torque on the coil is. So in this case, we are given, you can say, xz plane. So we can draw an approximate figure for that. So this is our x, and we have z, and the torque, we can say the coil is at an angle of 45 degree about the z axis. Okay, so it means if it is 45 to z axis, it will be also 45. So we can draw an approximate. This is our coil. Okay, and the angle is our 45 degree. And the magnetic field is along x-axis. So there will be torque induced in this current carrying conductor and coil in this case, and the torque is given by tau is equal to NIAB sine of theta. Okay. So you can say torque on a current carrying conductor, torque on a current carrying coil in a magnetic field that is of tau is equal to NIA B, and we have this as sine of theta. So A is the area of the coil, so we can find out its area. So A is the area of coil, and which will be equal to 5 times 2.5, and this comes as 12.5 centimeter square and can be written as 12.5 into 10 to the power minus 4 meter square, and the angle of theta is about 45 degree. So we can easily substitute all these values. We get as tau will be equal to 100, number of turns, current is given as 3, and area we just found it is 12.5, 10 to the power minus 4, magnetic field is given as 1, and here we have sine of 45. So this torque can be written as this will be over 300 multiply by 12.5 into 10 to the power minus 4, and this is our 1 upon square root of 2. So this torque can be approximated as 0.2828 Newton meter. So the option number is A is the correct one. Option A is correct. Now we come to the next question. Next question, it was also asked in the year 2019 mains, and it states that a rigid square loop of side A carrying a current I2 is lying on a horizontal surface near a long current I1 carrying wire in the same plane as shown in the figure. The net force on the loop due to the wire will be. So we have two wires, rather we can say one wire. First wire is carrying a current I1, and another one is the wire in the form of a loop, and that is carrying a current I2. And the loop is a square, so each side is given as A, and one of the closest wire of this loop is also at a distance of A from the long current carrying conductor. And because of this current I1, we can easily find out the magnetic field that will be on this square loop, direction of magnetic field. So the direction of magnetic field will be into the plane of the paper. So it will be into the plane of the paper. And let us suppose the magnetic field that is, let me name this is A, B, C and D. So magnetic field near this AD conductor, let us suppose is B1, and near the conductor BC, let us suppose that is our B2. Okay. And we have to suppose to find out the force, and the force, we know our magnetic field, and so we can write that the magnetic field at the near side is our AD of the loop, which we have said is our B1, will be equal to mu naught I1 upon 2 pi A. So therefore we can write the force on this near side, the force on the near side, if that is given as F1, then this F1 will be equal to I2 multiplied by A and multiplied by B1. And we substitute value of B1, so we get our F1 will be equal to mu naught I1 I2 times 2 pi. Okay. And this force will be our, you can say, attractive in nature, because current is in opposite direction. Let me write it. Current is in opposite direction, so it will be repulsive. Current is in opposite direction, so we are going to have this as a repulsive. Therefore, the force, that is our F1, will be acting in this direction on this particular conductor, that is our AD. Now we can find out on the far side of the loop. We say magnetic field at the far side of the loop, and that we said is our far side of the loop, like we said, is a B2, and far side is our BC. Okay, far side is our BC. So we said our B2, and that will be equal to our mu naught I1 2 pi a, and total distance now becomes a plus a. So this gives us mu naught I1 divided by 2 pi, and this comes as now 2a. So we can find out the force on the far side. Force on far side, if that is F2, will be equal to I2a times B2, and we substitute a, we goes with a, and we are left with mu naught I1 I2 divided by 4 pi, and this will be, you can say, current is in same direction, so this will be attractive. Current is in same direction, so we can say it will be a attractive force. And therefore we can say we have our F2 that is in this direction. Now we have two sides, that is our CD as well as AB. Okay. And the forces that will be acting in these two sides will be of, you can say, equal and opposite. So they are going to cancel each other. Okay. Because current is flowing in opposite direction, so the forces acting on it, both the horizontal sides, will be in opposite direction and they will cancel each other. So we can say the forces on sides, and sides are our AB and CD. We have AB and CD are equal and opposite. Are equal and opposite. Therefore, they cancel each other. So we can say the net force that is a F will be equal to F1 minus F2. To substitute the value, we get this as mu1 I1 upon I2, sorry, mu naught I1 I2, and this comes as 2 pi minus mu naught I1 I2, and this comes as 4 pi. And this gives us that our F net will be equal to mu naught I1 I2, and the LCM will be 4 pi, So this will be our final answer. Yeah. So it will be our I1 upon I2 and 4 pi, and okay, so we have this as a repulsive force because F1 will be greater than F2 because it is nearer to this current. So the option number D is the correct one. So this force will be repulsive because F1 is far greater than our F2. So therefore option D is correct. Option D is correct. We come to the next question. It was also asked in the year 2019, and it states that an insulating thin rod of length L has a linear charge density rho of x, rho naught x upon L on it. The rod is rotated about an axis passing through its origin, that is x equal to 0, and perpendicular to the rod. If the rod makes n rotations per second, then the time averaged magnetic moment of the rod is. So here the linear charge density is given as a dependent upon the x, okay, as well as our L. Therefore, and we are given that, let us suppose draw a rod. It is something like this, and it is being rotated about axis and perpendicular to the rod. So this is given as x equal to 0. So this is our origin, and we have a axis that is perpendicular to this rod. Let us suppose this is the axis about which it is being rotated. So therefore it will be forming some kind of circle. Okay. And the length of the rod is given as L. So L is the length of the rod, and for the sake of convenience, let us consider a small portion of this rod whose is dx, thickness is dx, and it is at a distance of x from the origin. Okay. And we have to keep in mind that here charge density is dependent upon our x as well as n. Okay. So we are going to find out that a small we can say element dx is considered. So therefore we can say that the charge in the small element dx, the charge in the small element dx, and that dx small element charge will be, let us suppose, dq, then this dq will be equal to the charge density multiplied by dx. We substitute the formula for our charge density. We get this as rho naught x upon L, and this comes as dx. So this is our small charge in the element dx. And based on this small charge, if it is rotating, we can find out the current element. Let us suppose that is di. You can say the current element, that is our di, will be equal to n times dq, and dq we already know, so we can write our di will be equal to n, and this comes as rho naught x upon L times dx. Now the magnetic moment element because of dx. So you can say the magnetic moment element and that is given as dm. So the dm will be equal to di and dA, and di we just found out that is our n rho naught x L into our dx, and our area is pi x square. So we can write that our dm will be equal to our, this will be coming as pi n rho naught x cube times dx divided by L. Now we can find out the total magnetic moment, that is our m. You can say our m will be integration of dm, and this is from 0 to L. We substitute value of dm, which is our pi n rho naught x cube L, and here we have our dx. So rest of the things will be constant. Only thing variable is our x cube dx, and this is 0 to L. X cube will be our x upon x4 upon 4. So therefore we can write our magnetic moment is equal to pi n rho naught L, and this comes as x4 by 4 and 0 to L. So it comes as pi n rho naught L and comes as 4, and this will be our L raised to power 4, and this L goes by this 4, leaving us 3. So we get our magnetic moment will be equal to n pi rho naught L square upon 4. This is cube. So this is our required magnetic moment, and the option that is our correct one is the option number is pi by 4, and option number D is the correct one. Option D is correct. So we come to the next question, and in this question it is also asked in 2019 mains, and it states that a moving coil galvanometer having a resistance G produces a full scale deflection when the current Ig flows through it. This galvanometer can be converted into an ammeter of range 0 to I0 by connecting a shunt resistance Ra to it, and into a voltmeter of range 0 to V volt by connecting a series resistance Rv to it. Then we have to find out which one option will be the correct one. in this case, we have to first of all convert the galvanometer into an ammeter. So let us solve for the first part. And in the first part, galvanometer is converted to ammeter. And of range 0 to I naught. So we can draw an approximate figure for that. So this is our galvanometer, and we have to connect a shunt resistance in parallel to this galvanometer. So if I naught is the current, then Ig will be the current through the galvanometer, and the shunt resistance S, and the current through the shunt resistance will be our I naught minus Ig. And this is given as Ra. Okay, shunt resistance is given to us as Ra. So as both are in parallel, so we can say that voltage across the galvanometer will be equal to voltage across the shunt resistance. So we can write that our Ig multiplied by the galvanometer resistance is equal to, we have this as shunt resistance as Ra, and this comes as I naught minus Ig. So therefore we can write from here that our Ra will be equal to Ig into G, and this comes as I naught minus Ig. So this is our first part. And the second part, it is said that we have to convert galvanometer into voltmeter. We have galvanometer is converted into a voltmeter of range 0 to V. And so we can write that our V will be equal to galvanometer current plus G plus series resistance, which is given as Rv. We can also draw an approximate diagram for it. So this is our galvanometer, and we have series resistance, that is in this case given as Rv, and we have the galvanometer current. It is like this, and we can write that our V will be equal to G times I naught, and this comes our Ig, and we are going to G plus our Rv. So we can easily find out our Rv from here. So we can write that our Rv is equal to G times I naught divided by Ig and minus of G. We can further simplify it and write our Rv is equal to, we can take G as common and take in LCM, we get this I naught minus Ig and divided by Ig. So this is the value of the series resistance that is to be connected across through the galvanometer. Okay, and we have to find out the product of Ra and Rb. Okay, So let us call this as equation number 1, and this is our equation number 2. So we can write from equation 1 and 2. From equation 1 and 2, we can say that our RA multiplied by RV is equal to G square, and we need also to find out the ratio. So RA upon RV will be equal to, this is our IG divided by I naught minus IG and its whole square. So the option that is the correct one is our option number B is the correct one. You can say option B is correct. We come to the next question, and in this question it is said that we have a so this is also related with the galvanometer asked in the year 2019, and it states that a galvanometer of resistance 100 ohm has 50 division on its scale and has a sensitivity of 20 microampere per division. It is to be converted to a voltmeter for 3 ranges 0 to 2 volt, 0 to 10 volt and 0 to 20 volt. The appropriate circuit to do so is. So in this case, basically we have to find out what will be the, you can say, range of this value R1 and R2, and given as in figure. So in this case we are given that basically it means that we have to find out if it is in the range of suppose of 2 volt, then we have to find out what will be the value of the series resistance, because now this will be our complete circuit. The second part, let us suppose we have to convert into the range of 10 volt, then this will be our entire circuit, and similarly it goes for the 20 volt. Okay. So we are given the information that the galvanometer resistance, that is G is given to us as 100 ohm, and number of division is given as 50. Number of division is given as 50, and sensitivity is of 20 microampere per division, and the voltage range, there are 3 voltage ranges. Okay. And we have to do it for a full scale division, for full scale deflection rather. Okay. You can say that for full scale deflection, current, which is basically our galvanometer current, that is our IG, is the product of number of division and the sensitivity per division. Okay. So the current IG is, you can write IG is the product of number of division and sensitivity per division. Sensitivity per division. And galvanometer is converted to a voltmeter when the resistance is added in series. Okay, so we have to remember that also. Galvanometer is converted into voltmeter, a series resistance R, let us suppose Rs, is added. And the value of series resistance we can easily find out if required, and we can say that our value of this Rs will be equal to V upon Ig minus G. So therefore, let us first of all find out our Ig. So our Ig, like I said, is the number of division, which is our 50, and the sensitivity, that is our 20, and 10 is to the power minus 6. So this gives us a 10 is to the power minus 3, or we can say 1 milliampere. Now we have three different, you can say, voltage ranges. Accordingly, we are going to find out Rs for three different values. So we can say first is of Rs1. So in particular, this case it is written as R1. So we can say this is of R1 is equal to voltage range. First is about 2 volt, and this is a 10 is to minus 3, and we have minus of 100, and this comes as 2000 minus of 100 and coming as 1900. And similarly, we can find out our second, that is Rs2. In this case, that will be R2 is our 10 divided by 10 is to minus 3, and this comes as 10,000 minus 100, and this gives us 9900, and this will be in ohms. And finally, we have our Rs3, which will be our R3. Now the voltage range is of 20, so this comes as 20 and divided by 10 is to the power minus 3 and minus of 100. So this comes as 20,000 minus 100, and this will be giving us 1999 and 00 ohm. So we have R1 of 19. So we have R1 of 19 and R2 is of 99 and R3 is of 199. Okay, so option number B is the correct one. Option B is correct. So we come to the next question. It was also asked in the year 2019 mains, and it states that a magnetic field of a plane of EM wave is given by B naught cos of kz minus omega I unit vector plus B1 cos of kz plus omega t j unit vector, where B naught is 3 into 5 into, sorry, yeah, this is a mistake here. So this has to be 3 into 10 raised to the power minus 5. 10 raised to the power minus 5. And B1 is 2 into 10 raised to the power minus 6. The RMS value of the force experienced by the stationary charge Q, which is 10 raised to the power minus 4 coulomb at Z is equal to 0, is closest to. So in this case, we are given a magnetic field that is being represented in the form of a EM wave equation, and B naught and B1 are given to us. We have to find out the force experienced by a stationary charge. So its velocity is equal to 0. Okay. So we can say that force on a charge, moving charge rather, moving charge due to magnetic field if given as our FB, then this FV will be equal to charge is given as Q, V is the velocity, and cross B. But the charge is mentioned as stationary charge. So we are given that it is a stationary charge. So which basically means that its velocity will be equal to 0. And velocity is 0, so force because of this magnetic field, or we can say magnetic force, will be equal to 0. Therefore, we can say our FB will be equal to 0. But the equation that is given to us is an EM wave equation. So obviously, there will be some kind of electric field that will be associated with this EM wave. So we can say, but there is an electric field let us suppose that is given as E, associated with EM wave, and force due to this electric field is given as charge multiplied by electric field. Force due to electric field is our Fe, that will be equal to charge multiplied by our electric field. And we know the relationship between electric and magnetic field. We know that our electric field is equal to c, that is speed of light, times the magnetic field. And for a sinusoidal function, let us suppose that is a cos of theta, then its RMS value is a upon square root of 2. So you can say for RMS value of a sinusoidal function, suppose that function is a cos of theta, will be given as a and square root of 2. So first of all, we are going to find out the electric field components that is related with magnetic field components, okay, because the equation that is given to us is about only the magnetic field. You can say the electric field components related to magnetic field components by the original relationship is our electric field is equal to speed of light multiplied magnetic field, and this can be extended to the respective components. So we can say that our x component will be speed of light multiplied by b of y, and our e of y will be equal to minus c b of x, because in the equation we are given as the component as I as well as our j, and we have to find out at z is equal to 0. At z is equal to 0, the equation is given as b is equal to our b naught, and we have this is cos of, we put z0, this comes as minus of omega, and we have this I unit vector, plus we have this b1, and this comes as cos of omega, and we have this as j unit vector, and we know that this cos of minus theta is our cos of theta, so we can write this our b will be equal to b naught cos of omega I plus b1 cos of, is there a t in the equation? Yeah, okay, in the second part it is t, first part there must be t here, I missed it, t, yeah, so this comes as t here, and we get this as omega t, and this is also our omega t but with our j unit vector. Therefore we can write that our electric field will be equal to, this comes as minus c, and we have it as b1 cos of omega t I1 plus c b naught cos of omega t, and we have a j unit vector. Now we can write our x component will be equal to c b1 cos of omega t, and our y component will be our c b naught cos of omega t. Now we are going to have a force in x direction as well as in y direction. So we can write that our force f of x will be equal to minus q c b1 cos omega t, and we have f of y is equal to q c b naught cos of omega t. So this is the force, and we are going to find out its magnitude resultant. So we can say magnitude, magnitude of the force if given as f will be equal to, we have this fx square plus fy square and its square root. We substitute the respective equations for fx and fy. We get this is minus q c b, and this is our b1, and we have cos of omega t and whole square plus fy is our q c b naught cos of omega t and whole square and its square root. So we can write that our f will be equal to qc and cos of omega t this comes as common. Inside we are left with V1 square plus B0 square. So obviously the RMS value will be given as the RMS value of F, that is our force, will be equal to our F max, and we have square root of 2. And we can write, or we can say substitute the value, we get F will be equal to, sorry, not F but RMS. So we have F RMS will be equal to minus 10 raised to the power minus 4, and we have this as 3 into 10 raised to the power 8, and then we have our square root of values, that is 2 into 10 raised to the power minus 6 whole square plus 3 into 10 raised to the power 5 minus 5 rather whole square, and divide by square root of 2. So this, the RMS value of the force will be approximately equal to 0.637 newtons, which we are supposed to find out. So this comes as option number C is the correct option. Option C is correct. Next question. It was also asked the year 2019 mains, and it states that the mean intensity of radiation on the surface of sun is 10 raised to the power 8 watt per meter square. The RMS value of the corresponding magnetic field closest to. So we have to find out the RMS value of electric, or it asks about magnetic field, and the relationship is quite common in it. So we can say for EM waves, intensity I is related to the RMS value of electric or magnetic field as, so we can write this as I is equal to, this we have half c, that is speed of light, epsilon naught, and this is our E square RMS, and in the terms of magnetic field, this is C upon 2 mu naught, and this comes as B magnetic field and its RMS ka square. And in this case we are supposed to use only magnetic field, so we are only going to concentrate on the second part of the formula. So we can convert from here and write that our B RMS will be equal to 2 mu naught times I and divided by C. We substitute the values, because mu naught is 4 pi into 10 to the power minus 7, C is 3 into 10 to the power 8. And we can write this as 2 into 4 pi into 10 to the power minus 7, and current intensity is given here. I is the intensity. Okay? So this is our intensity, not current. Intensity. This is given as 10 to the power 8, and divide by 3 into 10 to the power 8 and its square root. So this comes as approximately equal to 9.2 into 10 to the power minus 4 Tesla, which can be approximated as 10 to the power minus 4 Tesla, because the option number C is the correct one. Option C is correct. We come to the next question. So here it was asked in the year 2019 and states that a moving coil galvanometer allows a full scale current of 10 raised to the power minus 4 ampere. A series resistance of 2 mega ohm is required to convert the above galvanometer into a voltmeter of range 0 to 5 volt. Therefore, the value of shunt resistance required to convert the above galvanometer into the ammeter of the range is this. So we have to find out. Well, basically find out, first of all, we can say it is converted into galvanometer voltmeter range of 5 volt, then it has to be converted into a ammeter, and we have to find out the value of the shunt resistance. And galvano full scale current is given as 10 raised to the power minus 4. So we can write that our galvanometer current is 0.1 milliampere and voltage, maximum voltage range is our 5 volts, and the resistance R is given as 2 mega ohm. So we know that V is equal to Ig and this is G plus R. So this gives us our 5. Ig is our 0.1 into 10 to the power minus 3, and this is our G plus R. So this gives us that our G plus R is equal to 5 into 10 to the power 4, and we already know the value of R is given as 2 mega ohm. So we can write our G is equal to 5 into 10 to the power 4 minus 2 into 10 to the power 6, and this basically gives us that G is negative, and which is not possible. Okay, because from the first part, with the help of the voltmeter, we are supposed to find out value of G. So this will be giving us value of G, and then this value of G will be used for the ammeter part. But this G comes as negative, so which is not possible. So none of this option is correct. So there is some error in the question itself. So we come to the next question, and here it states that asked in the 2020 mains, and it asks that a magnitude of magnetic field in SI unit at the center of a hexagonal shaped coil of side 10 centimeter and 50 turns carrying current I ampere in units of mu naught I upon pi is. So this is our hexagonal, and we have to find out the magnetic field at the center of this hexagonal. So we can draw an approximate figure for that. So this is hexagonal, and let us suppose we have a center here, and assuming that the current is flowing in this direction. So all this hexagonal is basically combination of state conductors. So let us consider a state conductor, any one. So this is a state conductor, and we can find out that or rather we can say the current, sorry, not current, but the angle at the center will be of 30 degree, and side of this one side of conductor is given as A, and the perpendicular distance of this will be our root 3 A by 2. So let us consider one side and use the formula of one side of the conductor, and then we can multiply for its all 6 sides. Say magnetic field due to one side of hexagon let us call that as B1, and that will be equal to mu naught I, and this is 4 pi A, which will be the, let me write this as L, not A, length of the conductor, and here it will be sine of phi 1 plus sine of phi 2. Phi 1, phi 2 here is 30 degree. Okay. Now we simply substitute the values. We get that our B1 will be equal to mu naught I upon 4 pi, side is given as A, and here we have sine of 30 plus sine of 30. So this gives us that our B1 will be equal to mu naught I, sorry, L is the perpendicular length. So here it is root 3 A by 2. And this gives us that mu naught I upon 2 root 3 and A pi. So this is the magnetic field due to one side of the hexagon. Therefore, we can say that magnetic field due to, and the number of turns is given as a 50 turns. So we can modify it, and this gives us that the magnetic field at center due to all sides. So we can say this is equal to B will be equal to 6 multiplied by mu naught I upon 2 square root of 3, and this will be A pi, all sides, and n turns, and this comes as multiplied by n. Now we simply substitute the values. We get this as 6 multiplied by 50, and we have this as mu naught I, and our side is 0.1, so this comes as root 3, and we have here 2, and side is 0.1, and this comes as pi. So this gives us that we can just cancel it. This goes by 3. Here is root 3 and here is 3, so we rationalize it, and this gives us that the magnetic field this will be equal to 1500 divided by square root of 3 multiply by, okay, we have 0.1 also, yeah, so this is 1500, and we get this as mu naught I upon pi, and if we rationalize it, this will be root 3 multiplied by root 3. So this gives us 500 root 3 and we have mu naught I upon pi. Yeah, so we get the option number C is the correct option. Option C is correct. And we come to the last question of the 2020 mains, and it states that a charged particle carrying a charge 1 microcoulomb is moving at velocity 2I plus 3j plus 4k if an external magnetic field 5I plus 3j minus 6k into 10 to the power minus 3 Tesla exists in the region where the particle is moving, then the force on the particle is F into 10 to the power minus 9. We have to find out the vector of F. We have a magnetic field, so the force in the magnetic field is given as Q V cross B. So here mainly we have to find out V cross B. So we say magnetic force, that is our FB, will be equal to Q and V cross B. So we are mainly interested in finding out our V cross B. So for V cross B, this is I, J and K. We are given 2, 3 and 4, and magnetic field is our 5, and we have this as 3 and this is minus 6, and a common factor of 10 to the power minus 3. So we get this as cross product will be coming as minus of 30I plus 32J and minus K, and a common multiplier of 10 to the power minus 3. Now we have simply to multiply it by the charge. So we get F magnetic will be equal to 10 to the power minus 6. This is our 30I plus 32J minus 9K 10 to the power minus 3. And this gives us minus 30I plus 32J minus 9K and multiply by 10 to the power minus 9. And we are also given that this is our F into 10 to the power minus 9. So this gives us that our force F is equal, or value of F is equal to minus 30I plus 32J minus 9K. So the option number 30, 32 and minus K. Yeah, option number B is the correct option. Option B is correct. So these were the questions, total 10 questions. 8 of them were from year 2019 mains and 2 questions from the year 2020 mains. This completes all the 10 questions. Thank you.